I'll log in with another device. In a minute, I'm logging in with another device.
Yeah, no problem.
Recording in progress.
Yes. Okay. Yes. Now.
Good to go, sir.
Actually, this sharing the rights, I think you need to give to me. It is not allowing me to share this.
No, just 2 minutes. They will start the session formally. Then we will give you the right to share the screen.
Okay. Perfect.
Right. Yeah. Okay.
Perfect.
Good morning to one and all. I am Savitri H, Assistant Professor from Department of Mathematics, DSCE, Bangalore. It is a moment of extreme pleasure to welcome the participants to the first session of Day 3 Atal FTP on Computational Mathematics and Artificial Intelligence for Engineers. I would also like to welcome the speaker, Dr. Jagdish Chand Bansal. A warm welcome to you, sir. I am profoundly delighted to take an opportunity to introduce the speaker of this session, Dr. Jagdish Chandra Bansal. Dr. Jagdish Chand Bansal is an associate professor at South Asian University, New Delhi, and visiting faculty at Maths and Computer Science, Liverpool Hope University, UK. Dr. Bansal has obtained his PhD in mathematics from IIT Roorkee. Before joining SAU, New Delhi, he has worked as an assistant professor at ABV, Indian Institute of Information Technology and Management, Gwalior, and BITS Pilani. His primary area of interest is Swaram intelligence and nature-inspired optimization techniques. Recently, he proposed a fusion social structure-based optimization algorithm, spider monkey optimization SMO, which is being applied to various problems from engineering domain. He has published more than 70 research papers in various international journals, conferences. He has worked with the Indian Air Force and Liverpool Hope University, UK for various research projects. He is the editor-in-chief of the journal Methodox, published by Elsewhere. He is the series editor of the book series Algorithms for Intelligent Systems, AIS, and studies in autonomic, data-driven, and industrial computing, SADIC, published by Springer. He is the editor-in-chief of International Journal of Swaram Intelligence, IJSI, published by InterScience. He is also the associative editor of IEEE ACE published by IEEE, and Array, published by Elsewhere. He is the General Secretary of Soft Computing Research Society, SCRS. He has also received gold medal at UG and PG level. A warm welcome to you, sir. I request you to start your presentation.
Thank you, madam. It's my opportunity again. It's my pleasure to join the session again. And can you give me the rights for the name Jagdish C. Bansal, right? In which my video is not on to that screen. Okay. So. I hope my screen is visible now.
Yes, it is.
So everybody, good morning, and it will be great if the participants can switch on their videos. It will be good actually. It will have better impact. Over the 2 years, I realized that the online classes with video on give more attention. Actually, it's another type of pressure on the audience also to be attentive if the video is on. If not, then another kind of lenient. So it depends upon you. Not compulsory, but it will be better. Okay. So today's topic is the drone swarm, and in this lecture, I'm going to introduce what is the drone swarm, why it is important, what are the major challenges, what has been done in this area till now, and where it can be actually applied, real world applications of this, and of course the future research perspective in this area. What you cannot expect, let me just be frank, that you cannot become the expert of drone swarm after attending this lecture. But I promise that it will remove any kind of inertia of understanding this subject. It will motivate you to explore this subject further. If you people are in Bangalore, let me tell you, Bangalore is the hub of drone swarm, is the hub of drone industry, drone research at this moment of India. It is the number one, the Chennai and the Bangalore is the number one place where the research is going on, research and development are going on related to the drone swarm. So of course, if you are further interested in this area, you have the industry, you have the people just in neighborhood of you to explore further, to test your ideas there. Of course, I'm also testing my algorithms with one of the company in Bangalore. I'm in regular touch of them. They are implementing I'm visiting Bangalore for implementation and all. Of course, I'm a theoretician, so I develop algorithm, not the hardware. So everybody need a hardware person if a theoretician, and if a hardware person is there, then he needs some theoretician also who can develop the algorithms for them. So it is a big project, not single one can do the entire research on the drone swarm. It is a group, it is a research which can be done in a group, which can be done in a group of various expertise. You need a various expertise in this. Of course, I have only expertise in the algorithm, so I will more concentrate from the algorithm point of view. So let me tell you that what I'm going to tell you today. Why the drone swarm? What is the drone swarm? What are the challenges in developing the drone swarm? Then how the positions are updated in the drone swarm, how the drones in the swarm of drones, how the drones move from one position to another position so they do not collide with each other. Then the communication strategies in drone swarm. This is very important. There are many types of communication strategies by which humans talk to each other in the society. We are directly connected, we are indirectly connected in a human society. We are indirectly connected also and directly connected also. For example, whatever the things are going on, whatever the events are going on throughout the world, we are getting information from the TV channels, from the newspapers and various internet sources. And we are also getting the information from direct communication that Madam Radha Gupta called me that in my institute, this is going on. So I got this information. So it's a direct communication. So there may be many kind of communication topologies among the individuals in a swarm. And this communication topology is the major challenge when developing the drone swarm, one of the major challenge. I'll discuss those. Then various application areas, and many type of drone swarms are there. Not only one type of drone swarm, many type of drone swarms are there. We will discuss that also. Classification of drones means what kind of drones are there. It's not that great. Swarm intelligence majorly I have covered last time, but it is in the part of this also. So if the time will permit, I'll take few things on swarm intelligence. Otherwise, I will skip this. And then I will discuss what is the current status of swarm intelligence at the India and the world level, and what is the future of this. So this will be my idea, and I will try my best to cover as much as possible. Okay. The very first thing is, okay, I'll use the word DS for the drone swarm. I hope it's okay. Just for the convenience, I instead of calling again and again the drone swarm, I'll call it DS. So DS is important. Drone swarm is important. Why it is important? Let me tell you by an example. Forget about the drones. You may have heard of the self-driving cars, very famous. These days, Tesla is working. I think Google is also working on these self-driving cars. Now, situation that on the highway, when so many cars are self-driving cars, or all the cars are self-driving cars, just imagine this situation. And the time is not too far. Let me tell you, time is not too far. Why it is not too far? You know, just around 15 years before around 16 years before I bought my first car, at that time, nobody was thinking of buying a automatic gear cars in India. Everybody said, no, in India, it's okay to go ahead with the gear car, right? Manual gear cars. But now I see that no matter it's a small town or a big city, people are preferring automatic cars, and almost all the car manufacturer, all the models are coming in automatic automatic gear. You know, means that India is also adopting the latest technology. I assure you that in next 25 to 30 years, the self-driving cars will be realized, will be the reality in India as well, in India also. Usually, you know, it's a case study when, you know, when you hear the original developers of self-driving cars, they always refer India. They always refer India. They don't refer the Nepal or any other country. They refer India, that it will almost be the, you know, the greatest challenge for the self-driving cars, the Indian traffic. Indian traffic is the greatest challenge. But let me tell you, there is it looks like a random, it's look like a random traffic in India, but it is a chaotic, you know, in mathematics, you know that chaos is not random. There is some sequence behind it. But once we understand that sequence, then that chaos is also the predictable value. That chaotic sequence can also, through that chaotic sequence also, we can predict the value. So, you know, if we can have so intelligent system through swarm intelligence or through some other, we can have an intelligent machine which can understand that chaotic sequence immediately by observing the behavior of the traffic. Then of course, that can also predict the behavior of other cars, other car drivers. And of course, when all the cars will be the self-driving cars, then there is no problem. Everybody is everybody will follow the rules. So let me just take the example of self-driving cars to show you what is the why the DS is important, why the drone swarm is important. So just imagine the situation when all the cars are the self-driving cars this is a highway. Suppose this is a highway. Many cars are going on here, right? Are going on here, and then this car is there. One car is here. This car is moving at suppose 200 kilometer per hour. At this on this highway, it is moving, but it sees that there is a sharp turn here. There is a sharp turn, or there is some obstacle. There is some obstacle here. So this car, autonomous car, self-driving car, took a sharp break, quick break. It took the quick break. So at 200 kilometer per hour, it took the sharp, right? Okay. It has taken, there was some inconvenience to the passengers of this car. It has taken and it safely moved to this, or made an accident, whatever. It made an accident or safely moved, but there was some problem with this car at this particular time. Now, immediately, what if immediately this information through its sensors broadcasted to all nearby cars? This information is broadcasted because all the self-driving cars, if all these self-driving cars are communicating with each other, they are in a swarm, nearby cars, of course, nearby cars, not you are moving to the Bangalore highway, and of course not on Mumbai cars. They are not in the swarm, but these cars are in the swarm. These cars are in the swarm. So immediately, whatever is the experience of this car, if whatever the experience of this car, if this experience is immediately shared with other cars, then others car will started taking breaks before, much before the actual situation, without actually looking at that obstacle. They can take the breaks. They can take the breaks, right? And they can take the benefit of the experience of this car. What I want to tell you, that the members in a swarm can benefit from the discovery of others without actually experiencing that problem, without actually experiencing. So these cars have not experienced this problem, but they have taken the benefit of this, and they slow down themselves based on this, right? Based on this experience. And of course, these cars can safely move. Just imagine if they are in a swarm. If the cars are in a swarm, if the cars are communicating, all the cars on the highway at a particular location, suppose 1 by 1 kilometer, all the cars are communicating with each other, then there is a very few chance that there is an accident, right? Of course, this communication is through sensors, through network, some wireless network or something. There will be a communication then. Just imagine this situation. The same situation is with the drones. Many drones are there. Many drones are there. They are flying together. And here, this one drone is there. One drone faced some difficulty. Then immediately the information is shared with other, and other drones can immediately move accordingly. So that's why this communication is important. Overall, what happens? I always say this to establish the importance of the drone swarm. I always say, take this example. Just imagine a situation. If I'll be happy if you answer. There is a wall. A wall is to be made, and one person makes the wall in suppose 10 hours. Then 10 persons, if the 10 persons are allowed to make the same wall, then how many hours will take? How 10 persons will take how many hours? Can anybody answer me? One person takes 10 hours, then 10 persons will take how much time to make the same wall? Anybody can answer? If you people are listening, actually. If one person takes 10 hours to make the wall, then 10 persons.
Less than 1 hour or 1 hour.
Avinash, you're right. It is 1 hour or less than what you said?
It is less than 1 hour or 1 hour, because there are simultaneous activities involved in construction of a wall.
Yes,
When
great.
people are taking up.
Perfect. Actually, if it is if 10 persons will also make the wall in 1 hour, then it is not a swarm intelligence. They are not sharing the information with each other. They are not collaborating with each other. It should be less than 1 hour. Then we call this is an intelligence. If one person makes a wall in 10 hours, 10% will make wall in 1 hour. No swarm intelligence, means they are doing their job, no collaboration. But if they collaborate with each other, then a special kind of intelligence will emerge among them. And that intelligence is the swarm intelligence. So the wall will be made in less than 1 hour. Definitely it will be less than 1 hour if they are collaborating with each other. If they will collaborate with each other, it will definitely be less than 1 hour. That's swarm intelligence. So just imagine a situation of spraying the pesticides in an agricultural farm. Suppose you have an agriculture farm. This is your agriculture farm, and you have one drone. Suppose you have one drone only one drone. You have only one drone, and it takes, suppose, 10 hours. 10 hours to spray the pesticides, or just what is called inspection of this faulty leaves classification, that okay, at this particular area my crop is not good, or at this particular area the crop is good. So suppose the pesticides are to be sprayed on this farmland, then one drone takes 10 hours. If a person has 10 drones and they are communicating with each other, instead they have 10 drones. If there are 10 drones, then the time will be less than 1 hour. Time will be less than 1 hour. It will not be 1 hour. It will be less than 1 hour. Overall, the cost will be reduced. Overall cost of the spray will be reduced. Overall cost will be reduced. I hope you understand why the swarm intelligence is benefiting, why it is good to have the swarm intelligence instead of using one. Similarly, if you have very serious, Rawat got that accident, helicopter accident. The black box, people were searching that black box of the helicopter. That's in the given area. If something is to be searched, just imagine if something is to be searched, this is your global optima, this is your black box. So that is a global optima. I'm giving you some scenarios where the drone swarm can work better than the individual, can work better than single machine. Suppose this is your black box, which is actually global optima, and you want to search this within this area. Of course, if there is an accident, then black box must be within 1 kilometer by 1 kilometer area, or 2 by 2 kilometer, some area we can decide. And this is our search space. This is our search space. And let's 20 or 50 drones search in this area, and they are communicating with each other. They are collaborating with each other. So of course, if one drone is searching in 10 hours or 20 hours, then 20 drones can search in less than 1 hour. So quick search. Quickly they can search. Similarly, this is only about the black box, but there may be one situation when the time is very important. For example, some disaster, flood is there. If there is a flood, then of course you want to search the people in the given area, that survivors, and then to give the information of the survivor location to the base station, and so on. Overall, the information can be shared, the help can be provided in the minimum possible time if you have a drone swarm instead of a single drone. And instead of having 20 drones with no collaboration, the collaboration will give you better solution. So if you have collaborative swarm, that will always be beneficial, right? So swarm intelligence, the drone swarm is important. And I mentioned here particular, please consider that we also call them UAVs, or drones, come in a great diversity, and they are, of course, many type of drones are coming up. Upon the basic framework with their particular specifications, let's analyze the core characteristics of the drone swarm, we need to understand functionality, problems, and importance of the drones. Swarm of drones are fundamental future agenda and will be adopted with the passage of time. So, future is with the flying machines. Future of transport is the flying machines, right? Not the, the population is increasing day by day. Last time I was discussing this report, this industry report. So this industry report says that the global swarm intelligence market earned USD 10.5 million in 2017, the swarm intelligence market. And in next 5 years, it is going to get the compound annual growth rate of 28%. And why this such a great growth rate? And in next 10 years, it is going to get 36 point something percent, 38 point something percentage growth rate. And why this such a great growth rate of swarm intelligence is expected? Because of the autonomous devices and because of the robots, because of the drones. The robots and drones are, have wonderful applications in almost all areas of life. So I mentioned here that because of the drones and robot applications, the swarm intelligence is getting attention of the researchers and all the developers, industry also, and where these two things are majorly used: commercial, military. The increasing number of drones for defense. Actually, from last 3 years, I'm working with the defense also for the drone swarm, and I realized that in next 20-25 years, there will not be any job for the pilot, fighter pilot job may not be there after 20-25 years, because all the battles will be fought with the UAVs, unmanned machines, unmanned air vehicles, because instead of one big fighter plane, you send 100 drones, no risk of life, and they are very cheap also as compared to the fighter planes. They are very, very cheap as compared to those. So of course, everybody is in search of that solution. Okay. Why the drone swarm? Why the drone swarm? A common purpose for drone is military one, I already told you, but their civilian applications are attracting increased attention in the recent times. Civilian application, I mentioned few, I'll discuss in detail also. Low cost drones, the cost is also very, very important. The drones are coming you can buy a drone from 5,000 rupees to 5 crore rupees, right? Or even more than that. Like searchers are coming in, I think it is more than 50 crores searchers. So I just forgot the name of that technical name of the searcher. It's an Israeli product, but that searcher's endurance is quite long. It can fly around 8 hours, but not the drone, but not in the swarm category. Of course, the drones, the UAVs in the swarm, endurance, if they are in the swarm, the endurance reduces. Actually, endurance reduces because they have to collaborate. Their energy is going to in the collaboration. Okay, so what I want to tell you about this research paper. If you are really interested in the drone swarm, that I strongly recommend this research paper, which was published in 2018 in the Science Robotics Journal. This is a Science Robotics journal, very famous journal. And optimized flocking out of autonomous drones. Of course, when I'm calling the drone swarm, it is an autonomous system, remember. So autonomous drones in confined environments. In confined environment means in the well-defined environment. So optimized flocking of autonomous drones, not a single drone, it's a drones, swarm of drones in confined environment. So let me just take this video actually. Just a second. I'm switching to the video and will explain through one video from this research paper. Actually, there was one video file in this research paper. In supplementary file, I'll explain the actual concept of the drone swarm. Right? Let me show you that. Just can anybody just please confirm whether my this video is visible and the sound is also there?
Yes, sir. Yes, sir. It is there.
Sound is there?
Yes, sir.
Okay. So you can see here that this is the optimized. This is the same research paper. I just mentioned the title of the research paper. It's a optimized flocking. Flocking means flying, means collaborating with each other, with collaboration flying. Optimized flocking of autonomous drones. Autonomous word is very, very important. I'll define it formally in the next slide. So I'll explain the word autonomous again, why it is important in that case. Drones in confined environment. So listen, this is a full documentary around 5 minutes, around 5 minutes. So listen carefully, I'll explain also.
Video, we will present fully autonomous multi-drone flights with a fleet of 30 quadcopters.
So 30 quadcopters they are flying, 30 quadcopters. Quadcopter means 4 arms. 4 arms are there. So I'll explain you these this classification also. What is quadcopter? What is hexacopter? What is fixed wing? What is hybrid? I'll explain that. Time being, just consider it. They are the drones. They are the drones. So 30 drones they are flying together, right? Together, and they are not controlling them. There is no remote. There is no machine which is controlling them. They are the fully autonomous system, right?
They will fly in a confined area, avoid collisions with it.
Now, this confined area is actually the virtual GPS boundary. Let me tell you, what is this? You may say that, oh, it's not a wall. They are flying them in the sky or in the open area. So it's a GPS wall. Actually, remember, there is always a wall, GPS wall defined. So in the flight controller is a software which gives the autonomy to these machines. So in that flight controller, you can define the boundaries. You can define the boundaries that, okay, these are the coordinates, away you cannot go. So the drone will never go, even by manually, even if you will send that, it will not go. So that GPS virtual boundary is the confined environment, is the surrounded environment. So they are surrounded within certain area, right? But within that certain area, they are working
Each other and with virtual obstacles. This is a challenging task that has never been accomplished before due to its complexity.
Let me tell you that why he particularly mentioned and why I'm so much fascinated for this research paper, that he also mentioned the same thing, that this kind of complex work has never been done before this research paper. These researchers, these scientists this was the first attempt. They flown 30 drones together in autonomous way, complete autonomous way, and with that complexity. And I'll tell you what are these complexities.
We started.
Actually, you may immediately say that in India also there were many Soj where people fly so many drones together. But all the activities are predefined in that case. if I remember correctly, in on some, I think in the Allahabad Kumbh, there was a drone swarm. So the newspapers were saying that it's a swarm of drones. No, that is not a swarm of drones. They've flown some 100 number of drones together, and they made one movie name. They made some movie name. In IIT Delhi also, I know that group of researchers. They've flown certain number of drones, and they made some, some shapes in the sky with the drones. But all that is predefined. It is defined already, and on the predefined path, the drones are moving. That is not a drone swarm. Drone swarm means you are not feeding anything. Just leave them and give them the target that you have to reach there. You have to do this. You come back, avoiding the obstacles, right? How you move, in which direction you move, what speed you take, what altitude you will take, depends upon you. Then it is a drone swarm, right? So please don't get confused with that, with these simple group of drones. That is a group of drones, but it is a fully autonomous system.
Our project many years ago by studying natural phenomena that somehow exhibit collective behavior. Animals, for instance, like birds or fish.
So you can see here, he's explaining that how we flown those 30 drones. So he said that it's a natural phenomena by which we took inspiration. So in the last lecture, I mentioned about that natural phenomena, nature-inspired algorithm. So the same is here. The inspiration comes from there. Of course, I'm into nature-inspired algorithm, so that's why it attracted me to work in the drone swarms. So here you can see that. Just imagine that these are the drones or the birds. These six are the drones or birds. So they collaborate with each other. There is a collaborative behavior, collective behavior is there.
Control themselves by making decisions gathered from their neighbors, from local measurements.
So they take the decisions based on the information gathered from others and take the local decisions. Local decisions means this bird will take the decision that, okay, I have to move in this side, and this bird may take the decision that I have to move this side. This may be for time being, right? For time being. So the local decisions, and then ultimately the global decision, right? So the local learning and then the global learning.
And other individual decisions. Drones are our intelligent flying agents.
Drones are intelligent flying agents. If you remember, last time I started my lecture with this, that in nature-inspired algorithm, you design the intelligent agents. You design the intelligent agents. So through those algorithms, we are making the drones intelligent, right? And how intelligent? In taking the decision for their flying, for their flocking. And we are calling them the intelligent machines. So ultimately, we want to make the drones intelligent.
They are airborne. They make decisions based on the bio-inspired models that.
Bio-inspired or nature-inspired? I hope you last time also I mentioned the same thing, that you call them bio-inspired or nature-inspired. So when they took off from the land, they take the decisions. They collaborate based on the bio-inspired models. Now these bio-inspired models may be particle swarm optimization, maybe genetic algorithm, maybe CMAES. Actually, in this research paper, they use the CMAES, covariant matrix analysis evolutionary strategy. This is very, very famous strategy, CMAES, right? So that algorithm they have used in this research paper.
The uniqueness of our drone clock lies in the fact that they communicate with each other.
This in this research paper, or actually why I'm again referring this research paper, because this is a representative research paper. You can modify this research, you can update this research, but it is giving you the basic building block for the drone swarm. So here they are communicating with each other, and these communication links can be well defined. can be defined in advance or can be defined in autonomous way. So if it is autonomous only, then it is a complete autonomous system. If you define in advance, just imagine that you are defining this in advance, that this is okay. This is the communication strategy right now. Whatever is drawn here is the communication strategy. Then you can, I think I can draw, right? So no, I cannot draw this. No, it's not possible. So you can see here that this is the drone. If it collapses,
In the air.
In this video, we will present fully autonomous multi-drone flights with a fleet of 30 quadcopters. They will fly in a
sorry, okay. So if this drone collapses, if there is an accident with this drone, then this drone will be disconnected with the other drones, This drone will be disconnected. So the collapse of this drone will actually be the collapse of two drones. So you cannot define the communication in advance, right? And therefore, we need to define some strategy, communication strategy, that if it fails, you continue the communication via this rule.
Constantly, their flight is lidar pre-programmed and nor controlled by a central ground station.
Our goal today.
Look, this is one very important thing that they especially mentioned,
They
that
communicate with each other in the air constantly.
no control with the ground
Their flight
station.
is
Look,
lidar pre-programmed and nor controlled by a
no
central
control
ground
with the
station.
ground station.
Our goal today is to present the principal building block of collective motion. Our drones will fly in a tight formation and remain within a bounded area.
I already mentioned you this GPS wall. So this GPS wall is always there. That is because of that we are calling them the confined environment.
Yeah, they will also avoid collisions.
And there may be some obstacles also in the flying. So this is just they are simulating the real behavior here.
With each other and these virtual obstacles, similarly to natural systems.
And this is the simulation of the actual computer program which they made, right? So this is a realistic simulation of 30 drones. And you know, this connection, this is the just connection among them. They are communicating via these links, right? So you can see that whenever it requires, they divide themselves into smaller, whenever there is an obstacle, they divide themselves into smaller parts and then started communicating.
They will form coherent groups, split and reunite around obstacles and turn collectively around goals.
I suggest to see carefully for around 1-2 seconds that how these drones are turning. It's a realistic simulation, means actually the same thing the drones will do in reality, right? This is a simulation. Actually, we also developed a similar kind of simulation, but because of some, you know, the research paper is still not published, so I cannot show those simulations. Almost similar kind of situations we also have with NSGA2. We solved the problem with NSGA2, and we got better speed, we got better flexibility than this using NSGA2. Okay, so you see here that, you know, when this drone is coming here on this wall, then actually this drone has not reached to this wall. Without actually reaching here, this drone will change its direction. See,
task is that
that drone changed the direction. Means it understands that my other friends already met with the GPS wall or some obstacle, and this is the time to return. So that last drone has actually not seen the GPS wall, and still it returned, right? So they avoid the collision among themselves, means between them, among them, and with the GPS wall, with the obstacles.
On the front will always have to inform the others at the back in time to avoid crowding at the walls. This is a very hard.
This is called crowding, means do not make too crowd at the wall, right? So they start returning.
Task even for people. Similar situations in large football stadiums or concerts can cause accidents or injuries.
The novelty of our model is that we take into account the finite acceleration of the drones in their local interactions, which means that we can scale the model up arbitrarily.
This is one very, very important thing, because it looks very simple when you do the experiments in a simulation, when you talk theoretically, that whatever you are doing for 20 drones or 30 drones, the same thing can be done for 100 drones. But when you do it practically, it becomes really, really very difficult, because the communication nodes will increase, and once the communication node increase, the computational time increases exponentially. Just imagine this situation. Let me come back to this. If the communication, just imagine these four nodes are there. Just imagine that 4 nodes are there. Then this is one communication link. This is one. This is another. This is another. This is another, and this is another. Right? These are the communication links. Direct communication link. Everybody is connected directly with each other. So how many? 1, 2, 3, 4, 5, and 6. 6 communication links are there. 6 communication links are there. Just imagine you increase just one more drone, only 4 to 5. Then how many communication link will increase? 1, 2, 3, 4. 4 communication. 4. You increase one more. Then 1, 2, 3, 4, 5. The communication link will you increase just 2, and 5 plus 6, 4 plus 5, 11 links will increase. 11 communication link will increase. You have added only 2 drones, and the 11 links will increase. When these 11 links will increase, it means the number of signals coming to this drone will increase exponentially. You have increased only 2 drones, but the input and he has to give the information to those drones also. So the input and output will increase exponentially. So the computational time on the onboard computer will increase exponentially. So let me tell you, the scaling is very, very difficult. Scaling is very, very difficult. And to make that scaling possible, whatever you are doing for 30 drones, if you want to do the same thing for 100 drones, you want the same solution with the 100 drones, then you need to make that communication topology in such a way that it will not increase too much load on each node of the communication. This kind of topology where everybody is connected with everybody is called the fully connected structure, or the star topology, whatever you call them, fully connected structure. So the fully connected structures are not actually the practical solutions, are not actually the practical. I'm coming, these kind of challenges, are not the practical solution. And therefore, this is the job of now the swarm intelligence algorithm developers, that they define the new kind of communication strategies, so that with the increase of the nodes, the communication load should not increase to each node. So you understand that the onboard computer, you cannot put this heavy computational device on the drone. The weight will increase, endurance will reduce, right? So the onboard computer is very light. It cannot process too much information very quickly, and almost in real time. Response time need to be almost real time. Otherwise, there may be a collide with each other. The drones will collide with each other, right? So you need a quick response from each drone, and for that, of course, you need to define optimized communication strategies. So I was here.
To high speeds or a high number of drones without loss of generality or stability.
We always test our algorithms in a realistic simulation framework before flight and tune the parameters for best performance. We optimize our solutions with an evolutionary algorithm. Our aim is to maximize the speed and the coherence of
No, what we do with the swarm intelligence in case of drone swarm, the one thing I told you that communication strategies so that the response time is minimized. We also want to we also want to define the flocking in such a way that the speed is maximum. It says that you see here, the objective is to get the maximum speed.
Parameters for best performance. We optimize our solutions with an evolutionary algorithm. Our aim is to
Short initial.
Sorry. So this head, this is the head of the this research team. So he said that the objective, the optimizer for our problem is the evolutionary algorithm. Yeah, last time I mentioned these nature-inspired algorithms. So another category is evolutionary algorithm. Of course, evolutionary or swarm intelligence, because still the people call them evolutionary, but it's and they use evolutionary actually. We also used evolutionary actually NSGA2, which is in the evolutionary category. But of course, other algorithms can also be used.
Performance. Optimize our solutions with an evolutionary algorithm. Our aim is to maximize the speed and the coherence of the flock while minimizing oscillations and collisions.
So here they are showing the structure of the structure of the drone, how they get the information for the night flying. For the night flying, how they take the information in deciding the direction, or in the day flying also, how they decide the direction, right? How they are informing each other, with each other that what angle I'm going to take. When birds fly each other, so bird can see each other. So that my friend is going in this direction, let's move in this direction. So how the drones will see each other based on the color, and you can define some other kind of solution also, but they define this color combination. You'll see here that
when drones take off and switch from individual to collective behavior, they quickly find a consensus on the direction they will be heading. After
they quickly find the consensus of the direction in which they want to move.
Short initial phase of hesitation, they find consensus and fly away smoothly. The quality of our model can be assessed by how efficiently the drones are able to make collective decisions. In a highly optimized system, collective motion patterns emerge naturally and remain stable throughout the flight.
And to visualize the flight, we created a program in which...
So this is the... just to visualize the flight, that how they are actually taking the decisions. You see here that this person is moving this drone here and there, means changing the direction. So the color is changing. It means for each angle there is a color.
The color is determined by the direction of the drone itself. You can see that if I move around the drone with different directions, it will change its color.
This is the night flying. This is the real flight actually. Okay, so now let's close this and come back to our... So overall, I said that it's not that simple to incorporate these swarm intelligence principles to these unmanned machines. We need to develop, the challenges are too many considering the hardware limitations. Right now, when I joined that project, it was not clear what is the drone swarm. Any group initially, we were calling in any group of drones is a swarm of drones, drone swarm. It looks very fascinating word, the swarm, but we can't call any group a swarm. So this is the formal definition that and then I gave, that it is an interacting. The interaction among the drones is very important. So it is an interacting autonomous group of drones which is assigned to one or more tasks, right? Remember, it is not just for flocking, that just they fly without collision and that's done. No, they should be able to do some task, and the task may be some specified task. I told you that in the last lecture, I told you that we are good in teaching and research. The truck driver is good in driving the truck. He may not be a good teacher. We may not be the good truck driver. So similarly, you can develop a particular drone swarm for a special purpose. For example, the search in case of disaster scenario. You can develop a drone swarm in case of defense related problems. You can develop a drone swarm for the spraying of the pesticide in the agriculture farmland. That task may be different according to your situation. So it is an interacting autonomous. It is an autonomous system. It must not be controlled from the ground. It is also the requirement. It is not mandatory, but it is also desirable that all the drones should have the same configuration. It is expected that every drone has the same configuration and is able to perform tasks which anybody can do. Why I particularly mentioned this, actually, in my group of that drone researchers, we are a complete team. So I always insist on this. Usually what they do, they have a mother drone. Right? And there are many child drones. Usually this kind of drone system is right now available and very successful. So there is no harm in going with this. It's okay. Let's go with this. But why I'm giving more stress on this definition, that everybody should be equal. No mother child, no leader follower. Everybody should have the same configuration. And this is the necessary condition of swarm intelligence also, that all the individuals are homogeneous in that group. In the swarm, all the individuals should be homogeneous. So all the drones should have the same configuration. And why it is important? Just imagine a situation that this drone swarm you are using for the defense purpose. So the enemy know that this is your mother drone. So he will kill only this drone, and all the drones will be killed in itself. There is no benefit. There will be no benefit of having a drone swarm. It is as good as a single drone. This system is as good as single drone. It is not a drone swarm if the robustness is not there. It should be robust system. What is called self-healing. The system should have the self-healing capacity. Self-healing capacity means if the mother drone crashes, then any child can become the mother, and can continue. The mission is continued. Mission can continue. So yes, it is possible. This is possible that if the mother drone down, then any child drone will take the place of mother drone and can the mission is continued. I want to tell you that this is the desirable, and when we will have this kind of situation, we will have a perfect system of drone swarm. Very soon we will have this. Right now the problem is not at the algorithms level, problem is at the hardware level, and that's why, of course, hardware is developing. Everybody in the world is working in the development of the hardware. So what is the objective of the drone swarm? Why we require this drone swarm? Say, to develop an autonomous system. The objective is to develop an autonomous system. A group of drones, typically 30 or more. It should be 30 or more. Why?
Okay, recently, can you
I think mistakenly people unmuted. Okay, why I call that 30 or more? why I call them the 30 or more. Actually, there is a rule in swarm intelligence that there should be some minimum number of drones, minimum number of individuals in that group to have the swarm intelligence. And what is that minimum size? You know, to have the swarm intelligence, the swarm size, the swarm size should be greater than some minimum threshold, And what is that? Actually, I did some research on this theoretically and experimentally. Two types of research I did. I wrote a blog also on this. It was a very challenging task at that time. When initially I joined this team, then they said that, okay, how many drones we require minimum? At that time, I did this research and I wrote a blog. Also, you can just search on Medium. Medium is an online magazine. There it is published. I published it. It is there. So, there I mentioned that the minimum swarm size should be 10 actually. Minimum swarm size should be 10. Theoretically, it was found to be 12 actually, theoretically, but practically when we did, then it is 10 were also working. 10 were also working. So overall, I said that it should be equal to 10. Swarm size should be greater than or equal to 10. When I say that to have the swarm intelligence, 10 is sufficient. This doesn't mean that a 10 will give you the final solution. No, if you will increase this, you will have a better solution. If you will further increase, you will have a better solution. But it is not necessary that you keep on increasing and your solution will keep on becoming better. There will be some threshold after which it will not improve depending upon the search space. So I cannot give you the upper bound. Lower bound I can give. Upper bound I cannot give because it depends upon the problem. If your search area is suppose the entire country, then your swarm size may be in lakhs number of drones. If your search area is only your colony, then 10 is sufficient. If your search area is the entire Bangalore, then the search area may be 100, then the swarm size may be 100 or so. So of course, upper bound I cannot give, but the lower bound I can give that if you have less than 10 drones or less than 10 individuals in a swarm intelligence based algorithm, then the swarm intelligence algorithm may not work good. The intelligence may not emerge. Right? So the minimum, and it is found that for usually defense related purpose or the what is called disaster relief related purposes, there may be some avalanche, there may be some search of black box, there may be some flood, fire broke. In that cases, usually in that particular area, we need to search, and 30 is sufficient. 30 is sufficient, right? So 30 is very optimized swarm size, right? So we need to develop 30 or more. Connections among them is another important, that how to connect these drones with each other. So this connection is autonomous, this connection is flexible, or a fixed connection. Fixed connection and the flexible connection is very important, right? The ability to perform a well-defined task. Of course, this is the hardware task and other AI algorithms. For example, CNN or something, because you need the computer vision algorithms so that they can identify the human beings or particular black box. Some images of black box need to be given. The system need to be trained with that black box images, so that whenever the camera on board see that any such kind of image, it locked there, and they say that it is here, right? Okay. The swarm members should be able to communicate and collaborate, preferably without any central control. So I wrote it here, word preferably. Deliberately, I wrote it preferably. However, it is actually the necessary condition. In the swarm intelligence, it is a necessary condition, but here I wrote it preferably. Because right now, because of certain sensors and hardware limitations, this is not possible without any central control. So, some kind of mother drone is required, some kind of relay drones are required for having the drone swarm. The swarm should be an independent and autonomous system. It should be an independent and autonomous system which can find out the target in the complex landscapes. Okay. Now, the classification of drone swarms. What kind of drone swarms you can have? Look, based on this, that you have a central control or not, you have a mother drone or not. The swarm drones are classified into two parts. One is the fully autonomous and another is the semi-autonomous. Fully autonomous, semi-autonomous, and another category is the single layered and multi-layered. I'm coming to this. Fully autonomous means from the ground to the ground, from takeoff to the landing, everything is fully autonomous. In the semi-autonomous, what can happen? Okay, the flocking is autonomous, but the search is manual. After reaching a particular area, the search is manual. You are moving, you are guiding them. You are guiding them from the base. You are looking at the images and then guiding. Means whatever the image is feeded, suppose the drone is here and whatever the image is feeded of the ground to the ground station, right? And that ground station is actually observing the images, not the drone. Drone is not observing that it is a human or not a human, right? It is observed from the ground station. So these kind of systems are the semi-autonomous system. But if it is observed by the drone itself and it is taking decision, it is dropping something, or it is giving the information to the ground, okay, here I found the human is here, then it is a fully autonomous system. So these kind of systems, of course, our ultimate objective is to develop the fully autonomous system. Another category, and based on the mother drone or not mother drone, another category of the classification is the single layered and multi-layered. What does it mean? The single layer and multi-layered, let me tell you that suppose these are the drones. These are the drones. All are at the same layer. All are at the same layer means all are equal. All are equal. And everybody is communicating via some rule. Another category may be multi-layered. Multi-layered means these 5 drones are the slave drones, master drone, slave drone, or mother drone, child drone, whatever you call them. And these are the 3 drones, and then 2 drones, and then 1 drone. It is a multi. These 5 drones are actually communicating like this, and these 3 drones are communicating like this. Suppose this is the communication. And ultimately, this is the mother drone who is taking all the decisions, and all the information of all the drones is coming to this, and this is communicating with other. Means this is the center. This is the center which is giving all the information to everybody. You may call it wheel topology. This kind of topology is called in swarm intelligence, we call this as the wheel topology. Why wheel topology? Because this is your mother drone and these are the other drones. So this information is shared and like this. And they are taking the information, they are giving the information to each other, and it is analyzing all the informations and then guiding them accordingly. So it is called the multi-layered. But when all are communicating like that in that video I saw, so they are communicating like this, right? Means independently they are communicating. The links are flexible. Sometimes they are not communicating, sometimes they are not communicating. This is communicating with this, and so on. Then it is a single layered system. And let me tell you what we need: the single layer. This is our ultimate objective: single layer and fully autonomous. This is our ultimate objective. This is our ultimate objective. Now I want to tell you about this position update in the drone swarm. How the members in the swarm update their position. So here autonomous means the drone swarm should not be controlled by the ground station, but the direction and the distance to be covered should be decided by the drone swarm itself. This decision to be taken by information shared with each other. A typical update equation is this: x equal to x plus h. Let us call a drone by its position x, right? So this is one drone, and this its position, new position equal to old position plus this correction. And how this correction is defined? How this correction is defined? Let me call this the interaction of drones. And I'm this h is obtained by the interaction of drone x with all other drones. And usually now the definition of this h depends upon the topology of interaction, how this particular drone is communicating with other. So based on that, it will decide its final direction. You know, suppose this is your x drone and this is your x1 drone and this is your x2 drone. This x drone is communicating with these two drones. This x drone is telling me that you move in this direction. X2 drone is telling me that you move in this direction. What will be the decision of x? It can give some weight to this information, some weight to this information, and can finally decide this direction, right? So the typical update equation will be x plus the information gathered from this x1, from x2, and this h may be your x1 minus x or x2 minus x, or the combination of both. Or the combination means this x can follow this x1, x can follow x2, or the combination of both, or the combination of both. So here what I defined here, xg means I asked them that when this, I said that when x1 is telling me that you come in this direction, then I ask that what is your fitness. Then if x2 is calling me, then I ask them what is your fitness. Now if x1 fitness is better than x2 fitness, then I'm calling this xg, best, global best, right? So based on that, I'm following this drone. But this drone is also not blindly followed, right? I'm giving the weight to this, right? If it is telling me that you come here, and it is telling me you come here, then I will not completely come here, otherwise there will be a collision. So some value here, something here. So this t and this value of t may be less than 1, so that it will not superimpose to x1, otherwise it will be superimposed to x1. Okay, what are the major challenge? Most important challenge is the communication. I already mentioned you many type of topologies are there. You know, one is ring topology, one is called the ring topology, and one is called the star topology, and of course one is called the wheel topology, and one is called the von Neumann topology, right? So out of this, I realized that this ring topology is the best for the drone swarm. Why it is best? Let me tell you. What is this ring topology? That drones are considered in a ring. They are not actually in a ring. They are theoretically they are considered in a ring, and they will communicate. They are communicating with the nearby drones. Means this drone will communicate with these two drones because it is there near of them. This X2 will communicate with this and this, right? This and this. And this drone will communicate with this drone and this drone. It is called the ring topology. I tell you that till now it is a good topology. There are certain merits and demerits. I'm coming to discuss those. So let me discuss the merits and demerits of various communication topology. I think the most challenging task for the algorithm developer in drone swarm is this. Of course, for hardware developer, there may be some other challenges. A lot of things are there. That's not a matter of today's lecture to discuss the hardware challenges, but let me just think of this communication is topology challenges. So look, now the information sharing with other drones may not be practical idea. All other drones, I already told you that the onboard communication time will be very high, or therefore a less connected structure may be thought of. What I said, that if you consider a fully connected structure means everybody is connected. connected with everybody, then of course it is it may be very difficult. It may be very difficult for analyzing the information at particular node, and therefore less connected structure like this, like this. It is a less connected structure. It is preferred, but there is a problem in this, that if this drone is, down, if this drone is down, then this drone will also lose the connection with these two drones, right? So of course we need to develop a robust self-healing system as well as the less connected structure. For that purpose, many strategies are there. I propose few topologies. So just for I bear with me, I drawn it by hand and made it like this. So look, every drone is connected with the three nearest drones. So here you see, let me just take one example. I made many. These are the three, this, and this. Okay. So every drone is connected with these three drones, right? This is one group. This is one group. This is one group. So these four are connected. Every group is connected with other three. So total is 4. Neighborhood size is 3, means total is 4. So total 4 drones are connected with each other. 4 drones are communicating with each other, and these communication bubbles, these communication bubbles, as you can see, let me just make, this is another one. You can see this is another one. So these 4 are communicating with each other, and these 4 are communicating with each other. So you can see that these 2 are in common of this and this. So whatever the information these 2 have will also be communicated with these 2. But what is the benefit of this? That not everybody is communicating with everybody, and still they are connected. And why the 4 I have taken? Because if there is a problem that this drone is down, then at least another channel is there. Another channel is there for having the information about these 2 drones to these 2 drones, right? So some backup plans should be there. Some backup plans should be there in the communication topologies. Another communication topology, what I said, is the multi-layered, that you take one leader and it is connected with these 3, means only these leaders will communicate of various, they are not overlapping neighborhoods. Earlier there were overlapping neighborhoods, overlapping bubbles, but now they are not overlapping. These leaders are communicating with each other. These leaders are communicating with each other. This may be, but again there is a problem that if this leader is down, then the entire group will down. This is small group, this subgroup will down. Only these 2 will be connected then. Of course, this is also not that good. Now, to solve that problem, to reduce the communication time and to solve that problem, instead of having one leader, let us have 2 leaders simultaneously. So these 2 leaders are communicating with each other. These are the possible strategies that we can apply. Okay. The other important features of in the drone swarm, they are the challenges. I know the time is going to up. So they should maintain the minimum inter-drone distance. So what should be the minimum distance with each drone, so that they should not collide with each other and they keep continued in a group. If this is suppose 1 kilometer, the inter-drone distance is 1 kilometer, then they will not be in a group. If it is too close, then there is a chance that they can collide. So what should be the minimum distance with each other? Usually it is 5 to 20 meters. 10 meter is very good. However, right now people are keeping it 20 meter, around 20 meter. What is the maximum distance? Many drones are there. These are many drones. This is the maximum distance. What is the diameter of this? So that if they are too far, then they can lose the connection. They can lose the connection. So, this is called the aggregation. In swarm intelligence, we call that this is the aggregation. And this minimum distance is called the dispersion. So this aggregation, what should be the maximum distance? And so that they remain in the same network. These all are challenges according to the hardware available hardware. Okay. Application areas, security, survey, monitoring, surveillance. Maybe in future, in your residential society, you may not hire a guard. You know, you have the guards at your doors. Right now, guards are there. In future, there may not be any guard job. That this job can be done by the drone itself. It will recognize through, you know, you must have seen in your offices in Bangalore, very, you know, your photo, as soon as you enter to the office, you know, your photograph taken, you know, that face recognition system, through face recognition system, the gate is opened, come in. Similarly, on the society gates also, there may be a face recognition system, car recognition system, vehicle recognition system, and that drone can take those decisions accordingly. Can I take just 1 minute? There's an important call from my office. Just a second. Okay, so where I watch. The applications are actually in survey, security, survey, monitoring, and surveillance. A lot of applications are there. Of course, the disaster management, I told you that in case of disaster management, the drone farm can play a significant role. In fact, that Chennai flood, at the time of Chennai flood, these drone swarm helped a lot to the local authorities, helped a lot. I know the person who was helping at that time. So he was sending the videos and photographs at that time. During the time of the Corona also, they helped. Okay, search and rescue is another classification of drones. Actually, drones are coming in many ways. The based on number of propellers, how many propellers it has. So there may be 4 propellers, then it is called quadcopter, tricopter, quadcopter, hexacopter, octocopter. Of course, you may say that when you have the quadcopter, when the machine can fly with the only 4 arms, why you put 8 arms? To make the system robust. Sometimes what happens, the battery drains of one arm motor fails or something, then this octocopter can fly, can complete the mission, but not the quadcopter. If the quadcopter's one arm is not working, then it cannot complete, it will crash, right? So to make the system more robust, more arms are better. So usually these are classified into 4. Fixed wing, you must have seen the fixed wing means this kind of drones. Let me take the example. This is the figure. This is a fixed wing, right? Fixed wing drones. Merits is that they can fly longer distances, very high speed, and the demerit is that they require some terrain for the takeoff and landing, and they cannot hover at particular place. So hovering is a problem. The takeoff and landing is a problem. The benefit is that they can go with the high speed and cover longer distances. Endurance is high. The fixed wing with hybrid drones are actually the best solution for this. They can hover also because of these and they can take off and land also vertically. So they are called VTOL, vertical takeoff and landing, right? And the forward moving is through fixed wings. So they have the high speed as well as all the demerits gone. Single rotor is this helicopter design, so it is not that good. Multi-rotor drones, these are very famous. Everybody must have seen this. So they are very cheap as compared to the fixed wing. They are very cheap in price, very easy to handle. and of course very easy to fly also. Ordinary people without any much training, they can fly these, while the fixed wing and hybrid wings, the training is required. Okay, that's all from my side. I gave you that, I tell you that there is a lot of future of the drone swarms. It's a great future in case of the transport system, defense, disaster management of the drone swarm. I tell you that India is still in the race of developers in the drone swarm. It is not one of the top developers. It is still upcoming competitor. The best players in this are Netherlands, Dubots, Hydromea, Switzerland, US. China is also doing good. Of course, Taiwan, China, Japan, South Korea, all these countries are also doing good in this. And definitely we will also, in India also, we are doing, one ecosystem is being developed for the drone swarm, and you must have seen the news many times in the news channels or the papers about the drone swarm. Bangalore is the hub. If through this lecture I have stimulated your desire to learn this subject, I strongly recommend that you search the companies in Bangalore who are working in the drone swarm and contact them. They require the theoreticians. They require the algorithm developers as well. Thank you so much. Thank you so much. If you have any question, I'm okay to take the questions.
Participants, any questions? Any queries? You can interact with the speaker.
Yeah. If you have any question, just let me know.
Participants, do you have any questions? Okay, sir. I think we can
I think
wind up the
there's
session.
no
Yes,
question.
sir. Thank you so much, sir.
Can
Bansal,
stop
sir.
now. Thank you so much.
Thank you so much, sir. The session is very interesting and informative, sir. Thank you so much.
Thank you, ma'am. Thank you so much. Thank you so much. Should I stop now?
Yes, sir. Sure.
So we'll conclude the session. I would
Yeah,
like
Ms. Savitri, you can start thanking you.
I would like to thank all the participants for being a part of this session. I'm extremely thankful to the speaker. It is because of your support we are able to pull out this session with a great success. Thank you again for sharing your valuable, insightful inputs on swarm intelligence with us. Thank you very much, sir. And we'll resume the session after 5 minutes. I request all the participants to rejoin the session after 5 minutes. Thank you, and all.